So far, we've been looking at characterizing solutions with just one solute. Now we want to start looking at applying this to some chemical reactions. So when we're looking at dissolving a salt or looking at a salt that's in water, we're saying we need to treat this with an equilibrium. We have these equilibrium constants. But we want to remember that a system being in equilibrium means we have both the reactants and the product. So if I have something like sodium chloride that's dissolving into water, my system is only in equilibrium when I have leftover solid, right? The solution is saturated. So when this is saturated at that max molar solubility, and then I put some additional solid in there, that is a solution that is at equilibrium because I have some of my reactants present right in the mixture. I still have some solid NaCl2, and simultaneously I have dissolved ions, right? So I have both of those in there. So that means that this system would be in equilibrium. And there has to be solid for there to be equilibrium. But what about if I have a concentration that's below molar solubility, right? So sodium chloride saturated at 6.2 molar. What about when I have a lower concentration, which we certainly deal with a lot in lab? So 2.0 molar is below the solubility limit. If you make a solution of 2.0 molar, all of it dissolves. There is no solid that's left over. And we could think about, okay, well, we have NaCl as solid. When it dissolves, it makes 1 sodium and 1 chloride. So we know that that means that we have 2 molar concentrations for each of those, right? Sodium and chloride are both at 2 molar floating around in that solution. So then we can characterize how this solution will shift to reach an equilibrium by computing QSP. We know with QSP, we just plug in whatever the concentrations are actually at, which for sodium and chloride were both 2 molar. So we plug them in, we get that QSP is 4, which is less than KSP, right? KSP is given for NaCl up here as 37.9. 4 is lower than that. So this system needs to shift to product, right? I need to make more dissolved ions. But all of my reactant is gone. My reactant being the solid sodium chloride. I put in the 2.0 molar of the solid sodium chloride. It all dissolved. It just doesn't, it can't shift anymore. The system wants to shift to product, and it is impossible to do that because there's no more reactant. So when I'm dealing with solutions, I only have solid present if QSP would be greater than KSP, right? If it all dissolves, what would QSP be? And if I don't have solid, that means I don't have equilibrium. QSP is less than KSP. It just never reaches equilibrium. If I added more, it would all just dissolve. The system still needs to shift to make products, more dissolved ions. Just going to keep dissolving anything I put in until my QSP equals that KSP. So what I can do is that generally when we think about in the context of reactions, this would be forming precipitates. Is when does a solid form if we're mixing things together? And so we're going to be able to use this idea that QSP equaling KSP is the sign for the solid, the existence of solid, non-dissolved salt. We can use that to predict about how precipitates are going to form in a chemical reaction. So if I start, for example, with silver nitrate, the saturation, so the molar solubility is 1.5 molar. So 1.5 molar is my solubility limit, pretty high. If I have a 0.20 molar silver nitrate, that's below the solubility limit. So I would have no solid present, right? I just have a bunch of silver and nitrates floating around. But then I can mix something in with it that one of these might form a solid with. For example, chloride. I know that silver and chloride, we saw previously, has a low solubility limit, has a low KSP, so it doesn't tend to dissolve much. So if I put chlorides in the solution, I'm now going to have silver and chloride in the same solution. That's not something we're expected to find. So we might form a precipitate. Let's do it. You have 0.20 molar silver nitrate. What concentration of chloride must be established to cause precipitation of silver chloride? KSP for silver chloride is 1.8 times 10 to the negative 10th. So if we're trying to diagnose precipitation, we want to know when is some precipitation going to occur. We know it's when QSP equals KSP. And our KSP value is the 1.8 times 10 to the negative 10th. And we know that when we're looking at our QSP, KSP, right, we can just kind of use the same expression where it's equal to the concentration of silver times the concentration of chloride. Because I'm looking at a solubility product, it's always just the concentrations of ions. And I want to know the chloride at that equilibrium. KSP is a piece of reference information. It was given here, but even if it wasn't, you can always look it up. We're going to get tables of KSP that you can use. And then the concentration of silver is in the solution from the silver nitrate. So we should figure out how is the silver nitrate going to dissolve, how much silver is going to be in solution, look up a KSP, then we can solve for a chloride solution of when that sort of, when the precipitation will occur. So silver nitrate dissolves into silver cations and nitrate anions. It's a 1-to-1 ratio between silver nitrate and silver cations. So that means that the concentration of silver cations is going to be the same as the concentration of the solid. Right? It was 0.2 molar of the compound. So since it's 1-to-1, it's going to be 0.2 molar for the silver cation. So then I can just go ahead and plug in my values. KSP is 1.8 times 10 to the negative 10th. Silver was the 0.2 we just figured out. Rearrange and solve to get chloride concentration as being equal to 9.0 times 10 to the negative 10th molar. So what that number means is that this is the concentration of chloride that is required to be in solution with 0.2 molar of silver in order to cause precipitation. So if you don't want silver chloride to precipitate, you need to keep your chloride concentration below 9 times 10 to the negative 10th. So if there's any chloride, basically, in a solution, if you try to add silver nitrate, it's going to precipitate. So one of the implications of this is like if we prepare a solution of silver nitrate in the lab, we need to be sure to use as pure of water as possible, right? There's chloride in the water coming out of your sink. So if you're using tap water to make this solution, it's really low concentrations, 10 to the negative 6, 10 to the negative 7 molar in, say, tap water. That's super low concentration. Just barely any salt is in there. But it needs, if it's above 10 to the negative 10th, it's going to precipitate, right? So this is a sign where why we need to use as pure of water as possible when we're making solvents for a given solution. Because if there's anything in that solution, it's going to react if there's any possibility for that reaction. So we know that when you have a silver nitrate solution, if you add chloride to it, you're going to get a precipitation reaction. But the thing is, you can't just add chloride, right? There's no isolated chloride. Instead, it has to be in a solution with something else. So, there's like some sort of counter ion, right? We've seen this before, that when you want to use, you need to get an anion into solution. Well, it has to be in a compound with a cation. So, for example, sodium. So you could do a reaction of silver nitrate and sodium chloride, and then you get the precipitation formed, right? You get your precipitate that's forming here. It's silver chloride solid, and simultaneously, sodium nitrate is still dissolved in solution. If we take a look at this reaction, this overall reaction of silver nitrate and sodium chloride becoming silver chloride and sodium nitrate, we can come up with the net ionic equation where we represent the aqueous ionic compounds as their separated dissolved ions, right? Remember, we know that when you have an ionic compound and it dissolves in water, it actually exists as those separated ions. The solid silver chloride does not separate because that's not dissolved. It's a solid that has a left solution. It's crashed out, so it's now in this solid form. We then cancel out our spectators, the sodium and the nitrate, which do not change, right? The idea being that they're just kind of watching the precipitation. You started with a sodium ion, or sorry, that's nitrate ion, and you ended with nitrate ions that were isolated. Yes, it is changing which substance it's in, what compound it's in, but the local environment of the nitrate ion hasn't changed. So when we then end up with our net ionic equation of the Ag plus and the chloride becoming silver chloride solid, and that is the actual precipitation process, which you'll note is just the inverse of the KSP reaction. So the equilibrium constant for precipitation formation is 1 over the equilibrium constant, or over the solubility product, right? It's 1 over that. because it's just the inverse of the reaction. So in this, when we're looking at this sort of idea of will silver chloride dissolve, how much will stay dissolved, how much will be in the solid, it doesn't really matter from the perspective of like the ions, how the silver and the chloride get into solution. If you're starting from the solid, not much is going to dissolve. But if you start with a lot in solution, right, from doing a reaction, they all leave solution to get out, right? This equilibrium is always the same idea. Silver and chloride are in the solution together, some sort of ions, as well as in the solid that's not dissolved. And there needs to be a balance that's determined by the value of KSP.
Participation 1024, question 3. You have 0.20 molar PbNO32. You had enough solid NaBr to bring the concentration to 0.05 molar NaBr. Will any precipitate form? We have the reaction PbNO32 aqueous and 2NaBr aqueous becomes PbBr2 solid and 2NO3 aqueous. KSP for PbBr2 is 4.0 times 10 negative 5. This is the third question on participation 1024, due Friday, October 24th at 11:59 p.m. over on Blackboard. Link to the assignment is right below links to these videos. You have 0.20 molar lead-2 nitrate. You had enough solid sodium bromide to bring the concentration to 0.05 molar sodium bromide. Will any precipitate form? Lead-2 nitrate reacts with sodium bromide to make lead-2 bromide solid and sodium nitrate aqueous. KSP for lead-2 bromide is 4.0 times 10 to the negative 5th.
Okay, so this idea of predicting precipitation is something we always need to be mindful of when we're making solutions. We always need to be thinking about what is in any solution that we're looking at. So this actually applies to something we saw earlier this semester in lab. So FeNO3, iron 3 nitrate, is quite soluble in water. If you look up the KSP, it's really positive, it's a lot greater than 1. And the solubility limit is 4.3 molar. So you can get a ton of iron 3 nitrate to dissolve in water. One of the things we want to be mindful of is that water as itself does chemistry with itself. Not adding anything else into it, we know that water is always capable of autoionization. Two water molecules can become a hydronium and a hydroxide. And we know that their concentrations are very low under kind of in pure water. In pure water, you have pH 7, the concentration of hydroxide is only 1 times 10 to the negative 7th. So that's really low. Generally, it doesn't matter too much. But that means we now have hydroxide ions and iron 3 cations in the same solution. And iron 3 hydroxide is very not soluble. KSP for FeNO3 is 6.3 times 10 to the negative 38. So we would not expect to find a solution containing Fe3 plus and hydroxide ions. And there's not many hydroxide ions if you have a pH equals 7, but there's still some, and this KSP value is very, very small. So we need to be mindful of this interaction. So we got our KSP is 6.3 times 10 to the negative 38. If we have our, we want to figure out, is precipitate going to form? We know we have pH equals 7, so our concentration of hydroxide is 1 times 10 to the negative 7th. We can plug that value in. And the QSP we set is going to be equal to the KSP. That's where our concentration is determined by. And so we can figure out what concentration of Fe3 plus will cause precipitation of iron 3 hydroxide in a solution where the pH equals 7. And we end up getting 6.3 times 10 to the negative 7th molar, which is really low. And importantly, way lower than the 4.3 molar of FeNO3 that we would predict for the saturation. So yes, you can get iron 3 nitrate to dissolve in water, but then the iron will form a precipitate with the hydroxide ions that are in the water on their own. And so any dissolved Fe3 plus just starts forming a precipitate with hydroxide, right? You have to have less than 10 to the negative 17th concentration of iron. That's not hard to achieve. So you have to keep it, you have to have basically any iron, boom, you're going to start to form the iron 3 hydroxide, which means we need to decrease that concentration of hydroxide in order to preserve the solution. Because you're going to form a precipitate of iron 3 hydroxide out of this solution. It takes a little bit of time because there's not a ton of hydroxide, but it will start to kind of rev up and make more and more. This will happen more and more as you go. And so you'll start to get this precipitate. You'll lose iron 3 nitrate. This is a problem that we're going to need to deal with. And so we use nitric acid as our solvent. So when we did the determining KC lab and we studied the chemistry of aqueous iron 3 nitrate, we did it with nitric acid as the solution because there's so much acid in the solution that all the hydroxide is gone, right? It was like the solution is at like pH 1. And so then the concentration of hydroxide is 10 to the negative 14 or 13. Actually, it was at pH 0. So yeah, it was 10 to the negative 14. So it's even lower. And in that case, you can get the iron to dissolve because there's so little hydroxide that you can get the iron to dissolve. You don't need to worry about this chemistry. But, one of the takeaways from this equilibrium says, if you have a chemical reaction that can happen, it'll happen a little bit. If you allow it, if those reactants are in the same solution, they're going to react a little bit. Right? There's going to be at least some, and sometimes that snowballs into more and more and more, but you're going to get at least some of it happening. And that can impact your solution. That can cause problems you no longer have your iron 3 nitrate solution, right? You started to crash out. It started to be a problem. And so we need to, you've changed whatever concentration you thought you had of dissolved iron. So we need to be mindful of that and trying to keep it, we want to be sure that we have things correctly, set up, right? We always need to be mindful of anything that can happen needs to be accounted for.
Another participation question in this video. Will we maintain this pace? We'll see. Are there going to be 7 questions? I'm excited.